Okay, so I'll speak about the K-server problem and in general about online algorithms and some interesting questions that I believe are interesting. And this is joint work with Nikhil Bansal, Alexander Madry, and Sefi Naor. So what is computation? And I will not assume anything of knowledge. Computation, here in theory at least, is not playing games with computers, but just you have an input given to you, and then you try to compute some function. So sometimes you know how to compute this function, shortest path, and sometimes you know only to compute an approximate answer. And this is extremely useful paradigm for solving many problems. But for many problems in real life, it is not enough. So what it doesn't capture is some uncertainty that you have in life. So sometimes you want to compute a function, but this is some function over the stocks market or traffic, or we will see about fire trucks. So you have some uncertainty about the input, and you make some decisions in advance, and you cannot regret. So you are learning the input gradually, and then you make some decisions, and they are irrevocable along the way, and they affect your performance. So the question is how to approach this challenge of uncertainty. And there are two major frameworks for this. So first framework, extremely useful, is stochastic optimization. So here you essentially assume that your input is coming from some known distribution. And then what you try is to optimize the expected cost of your solution. So it's quite useful when you have a distribution, but in some scenarios there is no real, you cannot assume really that the input is coming from some distribution, or you don't know this distribution at all. So there is a second framework, which I will speak here, which is online optimization. In online optimization, it's nice, you make no assumptions about your input, and you try to optimize the worst case of the cost of your solution, which is really nice compared to stochastic optimization. The problem is that in many cases you cannot achieve anything meaningful. And it's surprising that you can achieve in some scenarios meaningful things here. So let's see an example. So here is a classical example, which is called paging or caching problem. So you have a small CPU cache, and you have a larger memory, main memory, and you want to cache here some of the pages in the main memory, probably the most useful ones. And again, the main memory is caching some of the most important pages from the disk. And in your computer, you have also the browser cache that cache some of the pages of the web, but of course not all of the web. So here is the concrete problem. So the concrete problem, at least from theoretical point of view, is that you have a universe of n pages. So think about n as very, very large, the number of web pages. And you have a cache that can hold k pages. K is much smaller, but might be quite large, the cache of your the main memory or the disk. But it is much less than n. And then this is what you hold. So now what happens is the game is as follows. You get in each round the page request that arrives. Here you get a page request for page number 5. Then you just need to bring it. So if the page is already in the cache, everything is good. And you bring it you use it. Otherwise, you get a request which is not in the cache. What you are doing is you fetch it from the disk. So you fetch it from the disk and you put it inside your cache. And this is called the cache miss. And this is what we would like to minimize, because it takes time to fetch such pages. And then you get another request. So here you get a request for page 8, and you don't have any more space in the cache. So what you need to do is to evict some other page. So you fetch page 8, for example, and evict page 5, and then you get it into the cache. So what you can see here in the example is that the only decision that you need to make is which page to evict when you have no place in the cache. You must bring the other page, and you need to evict some other page. And what you want an eviction policy which minimizes the number of your cache misses. So what do we mean by good eviction policy? We want some good eviction policy in the worst case. So we don't know the future, so the eviction policy only depends on the past request, on what we already see. But it will have an impact for later times. So we have no hope of matching the offline optimum. So the offline optimum is what you can get if you know all of the requests in advance. So what you want to is to design an algorithm which is never much worse than the optimal offline solution. So you look at your algorithm A, and it is called C-competitive if for every request sequence, the number of cache misses of A is at most C times the number of cache misses of opt on the same sequence. So this is what we mean good algorithm. Okay. So what can you get for paging? So for paging, here is a nice policy called LRU. So LRU meaning to evict the least recently used page. So you look at your pages, the one that is least recently used, you just evict it. And what you can prove is that this LRU policy is quite good. It is K-competitive. So if you think about it, K is quite nice because N, the number of pages in the world, is much larger, but still K can be 1,000. So you evict 1,000 times more pages than what you needed to evict. Not so nice, but the issue is that you cannot get better. So if your algorithm is deterministic, and we will see later what you can get with randomized algorithms, you cannot get a better algorithm for this. So the key reason why deterministic algorithm fail is that on some request sequence, the cache of the algorithm A, you should look at the lower bound, of course, but the main reason is that you look at how A behaves, and then in each round you have a uniquely determined cache. So you have some cache for certain sequence that you got, and then you can construct a sequence that causes this algorithm to fail in every round, while the optimal solution only have a cache miss every k rounds. So this is why the algorithm fails, and this makes you think that maybe you should add some randomization. At least from a theoretical point of view, it's helpful to think about randomization. So when you speak about randomization, what you measure is the expected number of cache misses. And you toss coins, so randomization is only on the coin tosses of the algorithm and not on the input. And then if you use such randomization, you can get a much better result. So, and why this? Because randomized algorithms are less predictable in some sense. So there is only, for certain request sequence, there is the adversary, if you think about it, knows only a distribution on cache contents. And then it is much harder for him to construct a sequence that will give us a cache miss in every point. So think about, for example, on evicting a page uniformly at random, although this is not a good policy. So using randomization, people managed to get a much better algorithm called marking, and then later on another algorithm which is optimal, which is order of log k competitive compared to the k, so exponentially better using randomness. And this is the best possible. Okay? Introduction to online algorithms. So we will speak here mostly on the k-server problem, which is a generalization of this problem. So what is the k-server? It's very simple, one slide. You have n locations with distance function. So think about a city with lots of crossroads, for example. And then you have k fire trucks that you need to handle in this city. So in each round you get a request, you get a fire that appears at one of the locations. So here is one file, it appears here. And then what you need to do is simply to send the server to this location. So if there is already a server at this location, you don't need to do anything. So you don't pay anything. Otherwise, you just move one of your servers to this point. So you take one server and move it, and then serve the request. And then you will get another file here, for example, and then you send another server to this request. So the goal here is simply to minimize the total distance, the total fuel that you are using to get the server. And if you think about it for a minute, you suspect that the greedy approach is a good strategy here. So greedy approach is just simply to send the track which is closest. So I'll just convince you briefly that this is not a good approach. So look here, you have a file here. So you send this closest server, and then you will get another file here. So you will send it back, and then I can continue with this approach many, many times, and you will pay eventually large cost, while the optimal solution that we compare ourselves to can just send another track to help. So you must send another track eventually, and not go greedily around it. Usually greedy is not working well in online scenarios. But if you send this track, you of course will get another request here. This is also something that happens adversarially. Okay. So why do we care about K-server? Not sure, but here are some excuses. So first, it captures variety of online scenarios. So think about servers as technicians or service tracks. It also captures some migration problems. And in particular, the paging caching problem that we saw earlier is just the K-server on a uniform metric. So think about locations as the pages. So you have n locations for n pages. And then when you get a request, you just you have just k pages in the cache. You need to move one of the pages. So you need to move one of the server to the requested page, and then you have a hit cost if you don't have a page at the same specific location. And also, actually, on the line, there is a good excuse for the K-server, some elevator. So there are lots of problems that this K-server scenario captures. But most of all, it's really a clean formulation of some problem, but it turns out to have a very rich structure. So I will tell you in a minute what is known, but it's not so easy problem as it looks like. And it captures probably the essence of what we want to understand about online computation, online optimization. So what is the status of the K-server? So as caching is a special case of the K-server, so you cannot hope to get better than K-competitive algorithm deterministically for every metric. And you cannot hope to get better than omega of log K randomized algorithm for the problem. And no better lower bounds are known. So there is no metric that you can say such that there is a better lower bound. And the big question is whether these bounds are tight. So the deterministic K-server conjecture states that there exists a deterministic K-competitive algorithm for every metric. And the randomized K-server conjecture is that there exists an order of log K, exponentially better, competitive algorithm for every metric. So essentially these are saying that paging essentially captures the whole complexity of the problem. I would bet that the randomized algorithm, there is an order of log K. The deterministic, I'm not sure, and we will get to this point. So let's see some history about the deterministic. So more than 20 years ago, there was the problem definition, and actually they considered the problem on k plus 1 points. So k servers and a metric of just k plus 1 points. And then there was a question, people start exploring this, and this was the first algorithm, k factorial cube. It sounds very, very bad, but this was the first algorithm that doesn't depend on n. And think about n can be very, very large. So maybe k is 10, but n can be 1 million, for example. And then this was later improved. And then in a breakthrough result, 94, there was a 2k minus 1 algorithm. Nice to state, less nice to analyze, but very, very nice results. And this almost closes the gap here. So in this deterministic place, we are done up to factor of 2. And although this 2 is not so important, it's quite annoying, and it's annoying for a long time. So it's quite nice to close this bound. And for this, I'm not sure if it's the upper or lower bound, actually. But for certain metrics, the problem is already closed. So there is a k-competitive algorithm for metric defined by a tree or by line, which is very nice and easy to state algorithm. So what about the randomized k-server? So this is much less impressive. So it started quite good. This is the result on paging that I told you about. An order of log k competitive algorithm and an omega of log k lower bound. But then not a lot of progress. So 9 years later, a polylog k competitive, but on a metric with k plus c points. C is a constant, so this grows very, very fast as c grows. And then there is some result on well-separated spaces, some very small metrics that are very far from each other. And then, quite recently, on the line, so line is quite simple metrics, n to the 2/3. So this is only better than the 2k minus 1 when k is very, very large. And then we found an algorithm, order of log k for weighted paging. This is on a weighted star metric. And then there is another result that I will speak more about in next slides, which is order of log delta. Delta is the aspect ratio on some binary HST with certain stretch. I will speak about it. And then even we managed to slightly improve this n to the 2/3 to something that is not polynomial, order of exponential in order of log to the half. So overall, what we have is the most general space that we know about good result is the weighted star, the weighted caching in order of log k, and then some on other variants, but the 2k minus 1 is still the best. So we have no proof that randomization really helps in many, many metrics, although we believe in this. And actually, we don't even understand very, very simple metrics. And this is true even after what I will say here. So we don't understand, for example, the line very well. Order of log k algorithm for the line is very, very nice result. Or two-level tree, we don't know even how to solve. So very, very simple metrics we don't know how to get. So what we got is that there exists an order of polylog, but in k and n, competitive online algorithm for any metric space. So this is a nice result, and it is better than the 2k minus 1 result when n is sub-exponential. You can compute it actually in k. So this O tilde hides some log n terms. Additional.
What terms?
Log n.
Log.
just swept to make it easier to look. So in general, it still depends on n, and we don't want this n because n can be much larger, but still an improvement. So what I'm going to tell you is briefly, so there are lots of details in this algorithm, and the paper is quite long. What I want to tell you is briefly what is the high-level idea in the algorithm, and actually from new results I hope to reduce 10 pages of proofs from the paper and make it a bit simpler. So the guiding principle here is that the arbitrary metric seems to be the hard part here. So we know how to solve things when they are really simple metrics, so like weighted star. So the idea is to trade the complexity of the metric for the complexity of the problem. So we reduce the k-server problem on arbitrary metric to a more difficult problem, but on a much simpler metric. This is the main idea. So I need to tell you a bit about HSTs, hierarchically separated trees. So what is such tree? This is most useful in online and also in offline scenarios. So this is a metric that is induced on the leaves of on the tree, and then what you have is that all leaves are at the same level, and the distance from each leaf to the parent is just 1. The distance from the parent to the next level is alpha, and then alpha square. Alpha is larger than 1. Think about alpha as 2, for example, here. And what you can prove is that you can take any metric and then randomly embed it in such a more simple metric, and then the stretch factor is an order of alpha log n. So what happens is that the distances are changing within a factor of order of alpha log n. So the main tool here in online scenario is that if you can find the C-competitive k-server solution on an alpha HST, then you need to pay only this alpha log n factor, and you get a randomized algorithm for general metrics. So this is what you need to remember. So let's take our k-server and look, what do we see? We embed our metric into such an HST, and then we try to look what happens here, what do we see. So as you remember, all our metric is at the leaves, so requests and the servers are at the leaves of the HST. So the question is, what do you see from here? And we will ask this for every node, but think about the root. What is the local view of the root? This is the intuition. So in the local view of the root, it sees the subtrees that it has, and then in the corresponding children, it has one server here and two servers here, and then it has some request here at this subtree. So what it should decide, the decision this node needs to make is how to redistribute these servers among the subtrees that it sees. And if it redistributes, then it pays some movement cost, because moving a server from here to here is expensive. So it can move a server from here to here, and then the local view is changing to this form. So, and the intuition, and we will see in the next slide, is that if you have more servers in some subtree, it will cost you less to serve the request in this subtree, because in general you will have more servers here. So here is the more specific. So the idea of Kort, Meyerson, and Poplawski, an algorithm that they did, was to get a k-server algorithm by combining some local algorithms like this and local views of the internal nodes here. So let's be more specific. So what they defined is a problem that we call the allocation problem. So think again about this root. You have D locations. These are your D subtrees. And you have K workers here that you need to redistribute every round. So you can have more than one worker in each location. And then you get a request. So what is a request? A request, you can view it as a project. So you have a project to do here. And then you get a sequence of heat cost or service cost. So H0 is the service cost that you will need to pay if you have no workers here. So this might be infinity, for example. H1 is the cost that you will need to pay if you have one worker, and then so on. So if you have more workers, you will pay less for serving this project. Okay? Now what you can do, you can rearrange the servers, the workers. So for example, you may take some workers from other nodes and put them here. And then what you will pay the heat cost here with 3 workers, and you will pay movement cost of 1 unit for each worker that you move. So this is the allocation problem. The goal is to minimize the cost, the total cost, which is the move cost and the heat cost, the service cost. Okay? Great. So you can note here, so it's not completely trivial to see that if you take heat cost infinity and then all 0, you can get actually as a special case the caching problem, the paging that we see. And we ignore, so think about it as an internal node, so we have more complexity that the number of available workers is changing over time. So we ignore this in this talk. So what can we say about the allocation problem? So the allocation, what they proved, essentially, so it's a bit more complex, but in a simplified form, it's that if you get an online algorithm, remember that you are working on a uniform metric here on the allocation problem, with heat cost, that for every epsilon, the heat cost is 1 plus epsilon, the optimal solution, and the move cost is polynomial in epsilon to the minus 1 and log k log n, the competitive, then this will give you a polylog k, n, and delta competitive algorithm for the k server. So delta is the aspect ratio. I won't get into this code. So the high level of the proof is, as I said, run some instances on the allocation problem at each internal node. And then the heat cost model the cost of serving the specific request in the subtree. And then recursively, you apply them recursively, and then you decode the number of servers in each of the leaves. So this is the high-level idea. I'll just say that this 1 plus epsilon is quite important, because in this recursive form, in this form, the heat cost is multiplied with the level. So you essentially get 1 plus epsilon to the height of the tree. So this needs to be quite small in order to get something meaningful here. So while the move cost, it is less restrictive. So you can just get polylogarithmic in n and k. So this is quite a good idea. All we need is a good enough allocation algorithm. And this is on a simple metric, so it's quite nice. The problem is that getting a very good algorithm for the allocation problem is quite hard. So what they managed to get is an algorithm for 2 locations. So allocation problem, but not on D locations, but only on 2 locations. And then they got some special, these special bounds that you saw about binary HST with some stretch factor, which is not meaningful for natural metrics. So the main question that was left open is how to get an allocation algorithm for a general case with D nodes. And actually we don't have a clue. So we know how to construct some algorithm, but not with the right guarantee. So the question is whether this is a dead end, and of course I told you that it's not. So the idea is to consider a fractional relaxation of the problem. So this is another nice idea that is repeating in online algorithms that I want to discuss. So what is a fractional relaxation or fractional algorithm? So fractional view versus the randomized algorithm. So what is a randomized algorithm? Eventually it's a probability distribution on states. At each time t, you can state some probability distribution on every state that you have. And then you have some way of changing it from time step to the next time step. And what you pay, the cost, is some distance between these distributions. So this is a randomized algorithm. Very simple. So for example, paging is just probability distribution on sets of k pages that you keep. In every time you set what is the probability of this set of pages in your cache and how this distribution is changing. K server probability distribution on set of k locations, or the allocation probability distribution basically on the number of servers you keep in every node. The problem is that this is sometimes very hard to construct. So it's very hard to construct right away a randomized algorithm that tells you exactly this distribution. So what we have is a fractional view. So what is a fractional view? You just keep some of the information. You keep only marginal values of the probability distribution. And then you define some movement cost between these marginals that is always lower than the cost of modifying any distribution which has these marginals. And picking these marginals is quite flexible. So you just need to figure out what is convenient for you. So for example, for paging, you can keep the probability of page P be in the cache instead of probability of the whole set of k pages. Or k server, you can have the probability of having a server in location I. So why this is nice? Any randomized algorithm and the optimal solution, of course, goes straight to a fractional view with lower cost. The problem is that this fractional view, you need to transform it back into a randomized algorithm, and this is sometimes hard. So you need to be careful, and sometimes it is very problematic to do this transformation. So what we do is we keep a fractional allocation problem. So what we decide to keep, we keep a track of the marginal probability xij of having exactly j servers in location I. So what you can see is that you have the following constraints. So think about these marginal. For every I and j, xij is of course between 0 and 1. But for every location, this is a probability distribution. So the sum over j of xij is equal to 1. And this is another constraint, linear constraint that I don't write here. The expected number of servers is exactly k. So these are the marginals. And accounting the heat cost is very easy because heat cost is exactly something that you multiply by xij. So it's just the expected heat cost. And the move cost, we define it's a bit more problematic, but it's some kind of earth mover distance between these fractional solutions. So the theorem that we prove in the paper is that there exists an algorithm for the fractional allocation problem such that for any epsilon, the heat cost is 1 plus epsilon opt, and the move cost is order of log k over epsilon opt, which is very good because, as I said before, for the allocation problem, if we get an algorithm like this for the allocation problem, we immediately get a guarantee for the k server. the main problem is that we cannot get from this algorithm an algorithm for the allocation problem. So this fractional relaxation is too weak for the allocation problem. So we have an omega of k integrality gap for it. So the question is what to do now, and the idea is that we don't actually need to solve the integral allocation problem. So only Meyerson solved it, but we actually don't need to solve it. What we can prove is to extend the reduction of Koch, Meyerson, and Poplawski to reduce fractional K-server to fractional allocation problem. So we extend this result and then use a fractional allocation problem to obtain fractional polylog Kn competitive for the K-server. And then we'll tell you what we are doing with the fractional. And then what we are doing after we got a fractional algorithm for the K-server problem, we just round it, we transform it into a randomized algorithm to an integral solution for the K-server, and we are paying only order of 1 here. So just where the integrality gap go, when we transform this fractional K-server to an integral, the K-server doesn't have this fractional gap. Okay. So we have another step here that I just want to state. It's very, very simple. So actually what we don't want this solution to depend on the aspect ratio. So in order to remove this dependence on the aspect ratio, we don't work with HSTs that may have a large depth, but instead what we take an HST and we transform it into what we call weighted HST, but with depth only order of log n. So in a weighted HST, the distance from some node to the father is not exactly alpha times, but at least alpha times the distance to the son. So we get some tree like this, and these are weighted edges. So what we need is everything that I told you. We just need to extend everything to a weighted star metric and not a uniform metric. And this is paying just another order of 1. So let's summarize the algorithm. So there are lots of steps. So here is the algorithm. The algorithm, you take your metric, you embed it, randomly embed it into an HST with stretch factor polylog n of n and k. So we need large stretch factor for the reduction to work, and we pay here for this. We pick a random tree to work, and we transform it into a weighted HST. This is just order of 1 distortion. Then what we get is a weighted tree of depth order of log n and distortion polylog nk. And then the main step here is to get a fractional K-server solution on this weighted HST. So here most of the work is hiding. You apply recursively the fractional allocation instances, the allocation algorithm that we have. And then what you get eventually is a polylog nk K-server fractional solution on this weighted tree. This, now I'm going back in the recursion, induces a K-server fractional solution on the HST. Here we lose the order of 1. And then this fractional K-server solution on the HST, we transform it into a randomized K-server solution on the HST. This is non-trivial, but not too hard. And we lose another factor of order of 1. And then this induces a randomized K-server solution on the metric M, the original. So quite a few steps, not too bad, I hope. So how much time do we have? 4 minutes. 4 minutes?
You have at least 5
minutes. Okay. So I will try to tell you for 3 minutes a bit about how we work. going some flavor about the fractional paging problem, which is easier than the allocation problem. So in the fractional model, you have a probability fraction xp, that page p is in the cache. And the total sum of fractions of pages in each cache is then less than k. And then at each step, what you need to keep is that the mass, the fraction on the current page requested is 1. What we take as a movement cost is just the earth mover distance between these fractional solution, and you can see that this is always lower than the cost that any distribution with these marginals will pay when it pays half for eviction and half for fetching. It's not so important. So basically, this is the drawing that you need to have with the fractional paging. And what I have time to show you is that how to transform, what's the problematic part of transforming a fractional paging algorithm to randomized paging. So think about fractional cache of size 2 that has 4 pages, and each one, the fraction is just half. So the distribution that this is the consistent with this is just with probability half page P1 and P2 and with probability half P3 and P4. But then think what happens if the fractional, if the marginals are changing to 1, x1 is 1, so you need to fetch page 1, and x2 is 0, so you need to remove page 2. So here what you have, you cannot bring page P1 to here because it already has page P1. So what you have to do is just to remove from here, for instance, page 3 and move it here and take here page P1. And eventually what it means is that each cache here in your distribution evicts one page and fetches another page. So you pay a cost of 1 instead of cost of half that the fractional solution is paying. So what you can prove actually in the case of paging is that indeed fractional paging can be transformed into a randomized paging paying this factor of 2. So this example shows that you instead, at least in some sense, you cannot get better than 2. We don't know how to get actually better than 2. So I don't have a lot of time to tell you about the algorithm. So I'll just skip to the conclusions. So conclusions. So what we have is a nice algorithm, I think, which is polylog in k and n for any metric. However, it's not perfect. So the great challenge here is to settle the k-server conjecture, which I believe you can get a log k algorithm. And actually, I don't think that these ideas are essentially the right ideas for solving the k-server. But there is a lot of other work. So first, get rid of the dependence in n. This will be very good because n can be very, very large. Or prove it is necessary. I don't believe it is necessary. But we actually don't understand very special metrics. So an algorithm for trees or for the line will be very nice here. Or shaving some of the logs here will also be quite nice. Okay, thanks.